Okay, welcome back everyone. In this video, we're going to talk about processes in robotics. Okay, so we're going to look at different processes that happen in robotics. We're going to do simulations on Tinkercad to do the same and learn the same as well. So it's going to be a very fun and exciting, lesson. I hope you all like it. And this is also going to be the part of our module 4 and the last part actually. So chapter 4 of module 4. After this, we're going to jump into module 5, which is going to be even more interesting, of course, because that's going to be more hands-on and more practical. But yeah, without any further ado, let's actually get into it and let's get started. So let's jump onto the screen. Perfect. So a little bit of, getting a little bit of understanding is very important. So that's what we're going to do. We are going to start with the definition of it. Okay. So Tinkercad simulations are, the ones that we're going to talk about. So we have already talked about this, that, they are simulations used for simulating things, simulating processes which are there. Specifically, we're going to understand processes which are there, which are involved. Okay. So we're going to understand the process in robotics and demonstrate how to create and simulate processes using Tinkercad. Okay. Now, when you say and when you talk about processes in general, okay, any sort of process that you talk about needs to have a couple of things which are very important. Now, those couple of things can be, the start, the end, and the main process itself. Okay. So we need to figure out what all these things are, okay? And we're also going to see what all different processes are there, okay? Now, processes are typically or generally involved when you're building a huge system, okay? And you need like small processes to make sure that the system is working as a whole, okay? So that's why we need all these processes. And that's what makes them, quite important and quite popular as well. And I'm not saying this out of context. It's more like a very popular and demanding thing. So if you know how to work with processes, I think you are pretty capable in robotics as well. Okay, perfect. That being said, let's actually see these processes. There are several type of robotic processes involved, okay, which includes, let's start with the first one, the sensing process. The sensing process involves acquiring information from the sensors and processing that information to make decision about the behavior of the robot. Now, we have understood the basic definition, okay, but let's dive into it with an example, okay, from Tinkercad, because I believe just the definition is not enough, okay. So let's take an example again, okay. Tinkercad is like, of course, fully loaded now. We are going to take an example of a sensor. I'm going to take the simplest sensor, this potentiometer, okay. Sorry, photoresistor, my bad. Yeah, and then I'm going to take an Arduino, okay. What I'm going to do is I'm going to move it here, and I'm going to put the photometer, something photoresistor. This is actually known as LDR, light dependent resistor. So I don't really have a huge practice of saying it's photoresistor. So photoresistor going one terminal to A0, second terminal to, let's say, 5 volts. Okay. And then I need a resistor to reduce the noise. If you remember, we have done this before, which is going to be 220 ohm, of course. Okay. And then I'm going to flip it like this. Perfect. And then put it over here. And then put the ground like this. Put this down like this. And we're done. Perfect. Now, let's go to our code. Remove everything that we have here. Perfect. And we're going to take the input tab, read analog pin A0, go to output, print all these things onto serial monitor like this. Close it down, start simulation. Okay, thing is, I think we have used too many components. So we might need to get rid of a couple of them. Okay, might make it easier. Yep. Okay. Let's go to our code. Open the serial monitor. It says 1. If you click on this thing and you move these values, you can see we are actually like changing, the input to the analog stick. Now, the way it works and the way it's important for you to understand is the fact that, whenever you're using any sort of controller or any sort of sensor, you're always going to have a process which is going to give you data. Okay. And when we are manipulating, working, or fetching data from any sensor, it's equally very important to understand that this data is non-interpretable right away. Okay. There's no meaning to it. Okay. What does 310 mean? Nothing. What does 1 mean? Nothing. You have to map all these values to figure out and conclude something. Okay. And that mapping system or the mapping process is something that we're going to talk as sensor process or sensing process as we over here. So sensing process is basically the one where we are acquiring the information from the sensor and processing that information to make a decision about the behavior. Okay, right now what we have done is only acquired the information. Okay, you see you can acquire the information right now, but you haven't made any decision. Okay, in order to make a decision, you need to go to control. Okay, and you have to add a condition. Okay, I think I'll take this one, really good one. I'll go to math and then put this one like this. Okay, then put the input again over here. Okay, so now what's going to happen is we're going to say that if the analog value is going to be let's say greater than 300, then I want to turn on an LED. I think I'll use a built-in LED high. Otherwise, built-in LED low. And to make it even more better, I think I'm going to add a weight so it actually works without any problems. Perfect. Now, if you see, this is the LED that we need to focus on, the L1, okay? When I click on this thing, okay, and I move it up, the moment it reaches above 300, it basically stays there. Okay. Okay, I think my bad. I used the wrong block here. I have to use the LED built-in to low. Then weight to 1. Perfect. This looks fantastic. And then as you move up or move down, you can see that it is essentially glowing now. You can make it more responsive if you reduce the wait time to, in milliseconds. I think 1 millisecond. That's just fairly enough to hold it and fairly not enough to, have it very slow. So now it's going to be comparatively much more faster. And you can see what we're doing over here. If you see the scene monitor, it's 310. The moment you bring it down to, let's say, 32, it's still working because we have set the limit as 300. So this logic building is basically the one that actually closes and creates the entire process. So right now what we did, we firstly are reading the data. Secondly, we are interpreting the data and telling and saying that, okay, this makes sense in some sort of way or the other. If you understand that this process is more or less involved in giving you a right or a better decision making system, that's absolutely true. Okay, and you can have multiple sensors. The only thing is you need to understand which sensor works in which way. So this sensor works this way. Even the soil moisture sensor works this way. So you have the same VCC, GND, signal port. All of these things which are there. You also have a couple of other sensors like PIR sensor, which is a passive infrared sensor. Again, almost works the same way. You just need to figure out, all the things that you need, and you can position of the object, of course. This is quite a popular sensor as well. But yeah, the whole idea is that whenever you're working with sensors, you need to eventually or basically understand that, all of these sensing systems or sensing delays are more or less, reliant or compliant with each other in some sort of way or the other. Okay. You don't really necessarily have the need or, the potential problem causing system because, sorry. Yeah. It's a lot of work. So yeah, so basically saying you don't really need to have switches at this point because technically speaking, if you have a switch, okay, switch is also a sensor. Okay, it's some sort of way you can say that's a sensor. So you can actually connect it to this and you can connect it to this as well. Okay, so you would have a switch and also a sensor. Okay, so if you play this thing, if I press the button, you would also get the same result as if you get this thing as well. Okay, so but the whole idea is that whenever you're adding or making a sensing system, it's equally very important to understand that sensing system are very much like a closed loop system. Now if you don't know what is a closed loop system, let's have a look over there. Okay, let's take some images. Now when you say open loop system, the open loop system is basically that you are sending a command to the controller and it's doing something. Okay, and you get the output. In a closed loop system, what happens is you send the command to the controller, it creates an action, and then you have a sensor that figures out if this action was actually performed or not. Okay, I'll give you a very simple example. Okay, let me actually come to my camera main. Okay, yeah, perfect. So let's say, hypothetically speaking, your mom told you to go out and bring some vegetables. Okay, in that case, you went out and got the vegetables and just kept it on the kitchen shelf. Okay, you didn't inform your mom and you didn't tell her that you actually have kept it. So there is no feedback. Okay, if there is no feedback, then it's known as an open loop system. Okay, next time you go to the market, go and buy vegetables, come back home, tell your mom that you got vegetables, and that's it. Okay, in this case, what happened is you add one more step, so that mom knows that you gave an instruction to mom. Mom gave an instruction to you, and she also got a feedback that the instruction is complete. The same thing happens in closed loop system as well. You told that you need some command to be done. Okay, and basically there's a sensor which checks if the command has been done or not, and then it tells the controller that the command has been done. Okay, so basically speaking, what happens is that you are having a system which can, or which possibly has the potential to take an input, okay, perform an action and give you an output. Okay, and this gives you a lot of more flexibility and credibility in terms of building the solution itself. Okay, so it's quite an important thing to do, I would say. Okay, and it's quite an important factor as well. So sensing systems are basically used whenever you want to create an open loop system into a closed loop system, because you always need a sensor. Okay, how do you know that it's sunny outside or it's not sunny outside? You need a sensor like the one that we were working on, light dependent resistor, to check if it's sunny outside or not. Okay, so all of these sensors are more or less the same thing. And if I jump back to my screen for a moment, if you search for a light dependent resistor, you can see you will find the same thing. Okay, so this sensor is essentially used to check if there is light falling on the sensor or not. Okay, it's a photoresistive material, okay, which basically checks and senses if there is any sort of light which is falling or not. So that gives you a basic idea. Okay, sometimes this light dependent resistor gets old. Okay, so then it starts to look like this because the material starts to erode and looks like blackish. Okay, like this one as well. Yeah, I mean, I think this is photographical problem, but usually they also blow out sometimes if you don't take care of them. They are essentially speaking, they're just resistors, right? I mean, a resistor can burn out in a lot of conditions. So yeah, but you need to know how this works and what exactly happens over here. Another important thing that you should know is that the thing that we were talking about, open loop and closed loop. Okay, and you would see this diagram in a lot of places in robotics. Okay, in open loop and closed loop. In the future, let's say you work with servo motors. Okay, servo motors. Okay, you would understand that servo motors are actually open loop motors. Okay, they are not really having any sort of feedback, or not all of them. Okay, some servos have a feedback, some servos don't have feedback. Usually industrial servos have feedback controller. Okay, there is another category. Okay, it's known as stepper motor. Okay, they don't really have feedback at all. Okay, so stepper motors never have a feedback controller by themselves. Okay, they just take input and they just spin. Okay, so stepper motors are there which don't really have feedback. Servo motors are there which sometimes have feedback. Okay, which most, sorry, my bad, most of the time had feedback, sometimes they don't. Okay, the reason is that servo motors are designed for a little more higher precision. Okay, but sometimes you need to make servos which are open loop servos. Okay, so you can also find open loop servos if you like right over here, open loop. Okay, so you'll find open loop servos. Okay, which don't really have a controller or a sensor to check if they're spinning or how much are they spinning. So you can find a lot of open loop motors as well, but stepper motors are essentially open loop servos only, so you don't need to find them. And yeah, you can actually buy them for pretty cheap if you are wondering. Let me open India Amazon servo. Yeah, you can buy it for like 127. I think this is for businesses, but a 151 or something, 200 or something, 284. Yeah, I mean it's pretty cheap. Of course, it's not that expensive. It's like for hobbyists and everything. So, but yeah, I think the whole idea is that once you have a motor, you need to have a lot more control, and servo motors give you that control. If you get like a stepper motor like this, then it's a different thing. Then it's like you know. So Yeah. So with the stepper motor, what happens is like, sometimes you get or you don't get encoder. But I think if you write for stepper motor encoder, I think you can find a sensor as well, which can fit into a regular stepper motor, and you can make it much more precise. But yeah, all of these things are like secondary, of course. The whole idea is that you need to understand that sensing systems are quite an important topic. Okay, and yeah, I think I gave you quite a lot of things and information to bounce. Let's go back and continue. Let's move on to our favorite one, actuation processes, my absolute favorite, and we are going to see one of the examples as well, of course, for this. The action process involves using actuators to perform physical actions based on the decision made by the sensing process. Now that we have taken a sensing data, okay, what you want to do is you want to actually get back this data and perform something. Okay, you want to, let's say, I don't know, I mean, maybe you want to perform an action, maybe you want to perform some sort of actuation. It can be anything, it can be any sort of process. The way it works is it's pretty straightforward again. You need to have a motor, let's say a motor or a buzzer. I think I'll take a vibration motor, it's pretty easy to use, that's why. So I'll take a vibration motor and connect the ground to the ground and connect the positive to pin number 13. Okay, now I'll give you a pro tip. If you are a robotics engineer, you should know that the onboard LED, the L13, the LED, okay, is connected to pin number 13 internally. Okay, so you don't need to change any code at all. So if you just start running your code and you change this value, the buzzer motor essentially like starts to work. Yeah, I mean, how, I don't know why is it like not being buzzing it off, but you can actually see it. Let me try with some other pin actually. Yeah, let me try with pin 12 as well. Pin 12 high, and then, oh, my bad. Pin too low. Perfect. And then I'm gonna move this. Okay. Technically, it should work. Let me add a multimeter to see if it's working, but we just can't really see it. Connect the negative to negative, positive to positive. Run the code. Press the button. Yeah, you can see it's sending out the data. That's why you have 2.5 volts being at the point or the terminal. So the whole idea is that, no matter what sensor you add, okay, the basic principle of a sensor is to perform an action. The basic principle of a sensor is to take sensing data. And the basic principle of an actuator is to perform an action. Okay, it can be a vibration motor, it can be a regular motor, it can be even an LED as well to show an indication. But usually it's mechanical actuations which are there. Okay, so usually motors are involved, so you can actually connect a motor. It doesn't really work that well because Arduino is not designed for running motors. It's designed for running giving signals. Then you need a driver to control it. So if you press this button, you can see the motor is spinning. In real life, this might not work the way it's working over here. The reason is motors are not directly runnable using Arduino. They need a motor driver to run. Okay, so that's why you need to understand that without a motor driver, it's pretty hard for a motor to actually take any action, perform anything. So that's kind of like a, what do you call, an important thing for any robotics engineer to understand that if you don't have a, what do you call, an action, then it's going to be a problem. Okay. That being said, I hope this give you a little bit of an idea. We're obviously going to take another example, to perform this better. Yeah, let me get rid of this, and get rid of this as well. Okay. Now you have quite a lot of actuators. You can have a servo motor as well. I don't really want to work with servo motors because they are like quite boring. I mean, you just plug and paste them over here, and they're. I mean, I think servo motors are quite boring. So I don't really want to work with them. But yeah, let's work with our favorite hobby motors and our favorite L293D. Okay, the motor driver that we all have been talking about. Yeah. Okay. Spin it, spin it, spin it, spin it. Perfect. Amazing. Ground. Ground. Okay, black color, black color. Perfect. Enable pin. Okay, since you're only working with 5 volts, I don't think so we need any extra voltage supply. But of course, it can be quite challenging in times. But right now, we don't need any problem. It should be just fine. Then we go to the output. Negative. Oh, my bad. Positive. Okay. Then we have the 5 volts. Perfect. This is done. This is done. Now we take the input 4, connect it to pin 13. It can be pin 12 as well, but I think I'll take pin 12 only. Okay, perfect. Perfect. And start simulation. Oh, we have a short circuit on the L9 3D. I think it's too much voltage, that's why. Okay, very understandable. Is 5 volt higher than the voltage at VCC? Okay, my bad. Sometimes, okay, I think I know what the problem is. The problem is we are having a port here, but we haven't connected this to that. So you have to connect this loop to that loop on the bottom. I know a lot of you might be thinking it's too complex, but it's not if you have practice in the previous ones. Perfect. Now we don't have any short circuit. Now, when I press the button, you can see the motor is spinning. Okay. And what we're doing over here is we're actually creating an actuation depending on the input that we're giving. So if there's light, we are actually starting the actuation again. Okay. If there's no light, then motor stops. Pretty straightforward, but very important to implement to understand what exactly happens and how it exactly happens. A lot of circuits don't really have this possibility to have the freedom of controlling multiple things. That's why you have motor drivers to channel this inputs and outputs and take care of everything, so that you can digitally and on the software control what is going to happen when. Okay, and that's also going to give you a lot more control over the hardware itself. Now, in this case, I can actually simply do this thing that I can, replicate the hardware, the sensing hardware again after I stop the simulation. Okay, copy paste it here. Okay, and then I basically take the terminal like this, paste it over here. The other terminal goes to A1. Okay, this one goes into yellow. This one is going to red. Perfect. And now we are going to connect another resistor, of course, which is going to go to ground and then to A1. Perfect. And in the code, I'm going to read analog A1 as well. And let's say I take the same condition. This time I'm going to actually trigger a different pin. Pin 11. Perfect. Okay. Start the simulation. If I change this parameter, you can see it's rotating in the other direction. Okay. If I change this parameter, you see it's going to go in the reverse direction. That's the power of having a very simplified circuit. I mean, I know it's not that simplified over here. It doesn't look that simplified, but it's actually very simple. But that's the power of controlling it using a driver. Okay, a mode driver gives you the flexibility of controlling the entire thing just by two pins. Okay, obviously you need to do a little bit of internal wiring, but yeah, in overall, if you see, we're just having four pins: two for power, two for data, and we're controlling a motor. Absolutely amazing, absolutely easy as well. Yeah. Perfect. So now we have understood a little bit of this thing. I think I'll add a little bit more onto this things to make it even more concrete, and then we'll move forward. Okay. So now let's extend this thing even more further. Let's add another motor, of course, and we'll use the same controller, the same driver. I mean, I'm going to connect the output to this output. Perfect. And this output to this output. Okay. Perfect. Now, since you have connected the output, you also need to connect the inputs. I'm going to take pin number 8 and pin number 9. Pin number 8, it's going to be yellow. Pin number 9, it's going to be green. Okay. Now you need to go to the code, go to the output, set pin high, set pin number 8 high. Okay. And output again, set pin number 8 to low. Perfect. Now we are pretty much done with this. Let's start. I don't know, sometimes Tinkercad just, is making some stupid decisions. I don't know why. Let's refresh it. Perfect, it's working now. I don't know what happened. Okay, it's already running. I think we have done something wrong for sure. Okay, pin it high, pin it low. Perfect. Okay, so you're not doing anything now. Let's increase the value. It's going in one direction. Perfect. Let's try with this sensor. You see both of them are going back. Okay. Now you can have built-in LED. Okay. Over here, or LED pin. We're gonna, what do you call? We have all done with pin 8. We're gonna do with pin 9. Pin 9 high. Pin 9 low. Okay, so you can see that both of these motors now are going on the same direction. Okay, so if it's a robot, it's going forward or backwards in one direction. And the moment you stop this, okay, and the moment you increase this, the other one, which is there, it's going the other direction. Okay, so what do we understand from this? Okay, we understand that physical mechanical parts can actually be very helpful if they are implemented correctly, and if they are being controlled using a digital controller. Okay, because right now all you need to do is just change a couple of lines. Okay, let's say at the same sensor you want one of the wheel to go in the other direction. How would you do that? Pretty straightforward, actually. I'll show you. Just change the high to low. Okay, pin number 9, high to low, or you can actually change just the pin numbers as well. Just change pin number 9 to 8 and just change this to 8. And you can just change pin this to 9 and this change this to 9 as well. Perfect. And now it's done. Let's see this now. Okay. And once you improve the slider, You can see one is moving in forward direction, one is moving in backward direction, which means the robot is going to spin at the same point. Okay, so that's what the beauty of all these mechanisms is. Okay, it's truly about understanding and boiling down to fundamental concepts, and then performing any action. If you don't have the fundamental concept capability, then it's always going to be a problem. It's always going to be a problem, because it's then it can get a little more difficult. Now, talking about difficulty and physical hardware as a general, we have seen now how physical hardware connects and controls different devices, of course, and at the same time you also have the possibility of controlling more motors as well. Okay, now imagine you have a robot with 8 motors or something. In that case, you want to control all of them at the same time. The only way that's possible is with the help of different motor drivers. Okay, so every 2 motors are going to have one motor driver which is going to control them, and which is going to give them direction and speed, direction, or which direction they want to go with, of course. And that's, without that, it's going to be pretty difficult for you to control all of these. Now, and coming to difficulty, another thing which is pretty important for you to know is that since these controllers are programmable, you can pretty much change the way you want your controller to work, okay, or the motors to work, because then you can, at the end of the day, you can just change the code, and you have everything run and ready. That's why a lot of robotics engineer, what they do is they finish the hardware first, and once the hardware is up and running, then they start working on the software. Because if the hardware is ready, then you can change anything you want from the software, because pretty much everything is software controlled, everything. Okay, right now you might not be able to feel it that much, because we are having basic robots, but in long term, or in bigger robots as well, we have everything connected onto the same hardware, and then we just change the software. That's as easy as it could be. Okay, now that we have talked about this basic understanding of a robot, and we have also understood, what exactly happens with this system, we are pretty much ready to understand and dive into our next process, of course, but also to look around into different robotic application, different robots that you can look for as well. Okay, one more thing that I want to show you all, since we are talking about this robotics and everything as well. I actually have another laptop. I think I will try my best to connect it to the screen somehow and record it, so I can show you what happens in a robotic system and a robotic operating system, ROS. Okay, and how does that work as well, just to give you a little bit of an idea, not to scare you or anything. Since you're already on this path of robotics, you might want to consider understanding those as well, and then I can share some resources if you want to learn robotics and ROS in particular. Yeah, that would be pretty great. Perfect. So that being said, let's actually jump into those areas as well and move as well. Let me swap my screen. Okay, so I tried connecting the laptop. It was a little difficult. So what I'm going to show you is, I'm going to show you from the ROS website. I think ROS Neotic is one of the most popular ones these days. I think it's going to go end of life. I think it is already on end of life. Yeah. End of life basically means that the support packages are not going to be updated anytime soon, because they are stopped. But ROS Neotic was one of the main distributions that ROS did. And yeah, pretty much ROS is a software architecture which is used for controlling robots, and it's pretty versatile actually. The good thing with ROS is that it allows you and allows people in robotics to do a lot of programming at a very fundamental root level. And the best thing is you can write in Python and C++ at the same time, and they work together as well. Okay, of course, when you're a proper robotics engineer, you will understand that C++ is the language that you want to work with, because it's so fast and so optimized, and Python is just not over there. Okay, coming back to ROS, you have a lot of processes. You can just start with introduction. What exactly is ROS? They'll give you a lot of idea. You can also go back to what do you call installation to understand how to install it. Then you can install the new one, which is there, ROS2, ROS2 Galactic and Rolling. I think Foxy is the most popular one. I have been using Foxy for quite some time now. Oh, okay. So support until May 2025. So this one is still running. That's nice. Okay, I misunderstood this. This one, Melodic, this old one actually got recently, discarded. So until May 2023. So this just happened. And yeah, but for this, I think this is still in support, so which is pretty nice. But yeah, I think still switching to ROS2 or ROS2 is a much more sensible thing, because they have a much more longer lifespan, and pros people continue to support them, even when they are expired. Of course, you can download the entire process. How do you get started with all these things? Pretty much very easy process actually. But yeah, I mean, just to give you an idea what exactly ROS is, how you can find these things, you can actually check out some of the more resources on my website. I'm amanmalhotra.com if you want. There's obviously no compulsion. There's a section of giving back. I have a channel which you can go from here, and you can also just subscribe, and you can also find the Discord community as well if you want to join. But yeah, no compulsion of course so far. But yeah, this just gave you a little bit of an idea of what ROS is. Now coming back to our, okay, we have the actuation process, and then we have the control process. Now this is basically the third process, or the control one. For this, I think I can give you a better example on MATLAB. Okay, so MATLAB is a highly extensive software for engineering, of course, and it takes the power of pure computing and pure logical building and control, and makes it quite versatilely available. Let's see if we have it running. MATLAB, okay, it's still opening, so maybe a minute or so. But MATLAB is pure engineering software. Okay, now it's on this monitor. But it gives you the freedom and control of an engineering toolbox. You can do a lot of optimization. You can do PID controllers. You can do, MPC controllers, and so many more controllers using this MATLAB software. It gives a lot more control to the robotics engineer, and to also to the developer when they're working on it. And I think overall, considering the MATLAB with its versatility, I think you can do a lot more things than in general. It also comes with something known as until it's load. So let me show it over here. Simulink. Okay. Simulink is nothing but a block-based diagram based system. So you can actually connect blocks to simulate a wind turbine, also to simulate a robotic arm, a lot of things which you can possibly think of. And this all happens just inside MATLAB. Okay, so MATLAB is like pretty much self applicable and self reliant. Okay, so you don't need to have any dependencies. I think it's another good thing that I feel about MATLAB is it takes the power of pure engineering and gives you the control that you need as well. So you can have the M files which is there, which you want. Okay, these ones are actually like for inverted pendulum. So I was just simulating inverted pendulum. And these are files for those. But yeah, I mean, you can find quite a lot of interesting use cases, quite a lot of interesting projects as well. You have feedback controllers. You have lots and lots of things inside over here in MATLAB. Okay, but again, it's quite a difficult software as well. It's not made for everyone. It's not easy for everyone as well. But it's highly recommended. If you want to get into research, then definitely. If you want to get into the industry, then maybe not that much, okay? Because MATLAB is not really used in industries because of its lack of, that much support into the integration, and also the costs that it comes with. MATLAB is actually very expensive. It's like one of the most expensive engineering softwares out there. And not really everyone wants to have something this expensive, being built every year or so. So a lot of companies don't really work with MATLAB that much, but it's still like one of the most popular choices. Okay, I think it's on take, so I'll just keep it loading. But yeah, that basically goes down to our control processes, and that also wraps the process part as well. Persistent Tinkercad simulation is important because it enables users to test and validate the process of robotic system before building the real world. Using simulations like tools like Tinkercad can save time and money and eliminate the need of physical prototype and testing. A simple example of this could be like simple robots which are there, of course. Okay, okay. Testing systems which are there, system which are the robotic arms, fine motor tuning. It can also have multiple robots in a swarm, and in conclusion, robotic systems which are there, conclude to Tinkercad and other processes. Okay, but coming back to this thing, I still want to show you a demo. So I would try my best to open this up. Yeah, let me see if we have some errors over here. I don't know. Let me try opening another case. Also Simulink MATLAB block as well. Okay, these are very heavy, by the way. And trust me when I say this, it's heavy because I'm using a very powerful Mac, but it still takes a lot of time. I think partially it's because I have installed pretty much every toolbox which is available on MATLAB. because it's pretty important to have all these toolboxes when you're working as a robotics engineer. Okay, but this is how it looks. Let's see. Perfect. Ignore. Okay, so you can see now we have, like a block-based diagram. Let me actually scroll up. Yeah, so you can put in your equations, you can put in your, derivative equations, put in all the transfer function values, put in everything that you can possibly think of, and it will solve it for you. And, once you run this command, let me run this off actually and show it to you. Let's open this scope. Okay, it's over here. Yeah, so you can open a scope like this. Okay. I think I need the parameter for these. I haven't really set this off. So let me get rid of this for now and run this again. Okay. You can see now the data is now getting generated, and you can see that the step function is now being built. Okay, so this is just a transfer function, of course, and a step function is nothing but one step. So if you see the value is reaching one and then stopping, okay, so this is a step function. A transfer function is basically can have a variation, and now what we're doing is we're trying to define the damping equation of this thing. I know it's a lot of maths, a lot of complicated words, but for the people who have already done this thing, they might be knowing what I'm talking about. But yeah, the main idea over here is that you are more or less having a block-based system which allows you to perform all these things at a much more better ease, okay, at a much more better control as well, without actually diving into a complex tasks and everything. Okay, so that gives you a lot more credibility in the market as well. So if you're a robotics engineer, that's just another thing. Perfect. So now let's move forward. Okay, moving forward, I think we concluded with this chapter. Let me come back to the camera. Okay, we have understood what exactly are processes. How do you know? How do you create these processes? What is the best software practice to work with processes, and how exactly you can achieve these things? Moving on, we are more or less going to move towards building a robot and having a task at the end, which is going to give you a lot more better control over what all you have learned. I'm also going to show you and share with you how you can also make 3D designs. I have a 3D printer, but I don't think so that's possible to 3D print right now. But I'll still show you how you can 3D print your designs and make them, bring them to life. But yeah, I hope and I'm glad that you did until here and made it until here. I'll see you all in the next one. Till then, happy learning and peace.